This is a review on the paper about gravitational deflection observations at a millimeter scale. And the abstract goes something like this. It's a well-known phenomena that gravitational lensing is observed around large objects like planets or stars, where the light is diffracted around the edges. Now, and it's also well known that the extent of deflection is a function of the density of the object. Now, this paper argues that would such a deflection be expected to be observed at a smaller scale in the order of millimeters, like around a pencil, for example. Secondly, would that also be a function of the density, right? So the scales are very different here, but still we propose an experiment which can attempt to observe such a deflection. So with that background, another point here is that this phenomena was well known even before the relativistic approach, right? By means of the Fermat's principle of light deflection, for example, which treated the region around this object as that of a varying refractive index, right? And hence it had its own treatment of in terms of refractive index. Now, with that background, we jump into the actual experimental setup and how can we be sure that this is error free, and how can it be replicated by more instances. So here's a diagram of the whole experiment. So there's a laser which could be a common diode laser, and then this object O is a cross section of a pencil lead, and there's a laser beam which is shown across the cross section of the pencil lead. So this beam will then diffract around the edges and also cause interference pattern on a screen at a certain distance away. So the whole experiment is, if everything were to be constant except for the mass density change between scenario A and B, then would we expect some changes in the interference pattern? So the reason why interference pattern is chosen here is it's very sensitive experiment, and it can record changes in the order of nanometers, provided the rest of the setup is stable. So let me bring up the specific experimental setup as well while I talk through this paper. So we use a commonly available green laser 523 nanometer laser diode, and let me bring that up here. So like that. This is a ordinary laser, but we have made some changes so that it can be controlled for intensity and so on, and it's placed on a rotatable head. So this is the source of light, and the object at which this interference happens is nothing but a pencil lead, if that's visible here. And this lead in specific is a 0.7 millimeter clutch pencil lead and of shade called 2B. So there are other shades available, obviously, and for example, here's another shade called HB, and the shades are created by a percentage change in graphite among these LEDs, which change the darkness profile of that LED. So this LED is actually now kept on a stable platform, like this heavy base here with the V-shaped grooves, two V-shaped grooves, and the LED is seated on top like that. So that way different scenarios are executed by replacing this LED, right, with another LED. Then we can expect it to be fairly at specific positions even in different So the image is captured at a distance of several meters. It's captured using a smartphone, which is not operated manually. It is operated using a wireless interface like Bluetooth controller to turn it on or capture the images. And these images are large number of images captured, let's say 50 to 100 images for one scenario, and then repeat it all over again for a different scenario. So yeah, before the actual experiment, there's a quick background around the theory around diffraction itself. It's quite interesting and long history, whereby diffraction today does not have a lot associated to the mass of the object that diffracts. It's really a function of the shape and contour of the edge around which the diffraction happens. There is some theory available which deals with the conductivity, but nothing to the nothing around the specific gravity or the specific density of the object around which the diffraction happens. So most of the theory available today is built on top of the Huygens principle, right, which dates back to 18th century, and then of course the Young's double slit experiment, which further built the interference theories. Prominent among them is the Kirchhoff's wave theory, and there's a nice archive around the entire series of derivations or changes which have happened to this theory in the past 2 centuries alone. And interestingly, there are other alternate theories like geometric theory of diffraction, which can better explain some of the scenarios dealing with odd shape of apertures. Now we go back to our observations based on the experimental setup which we described. The interference pattern on the screen, which is captured by the camera, is further processed using image processing software. Specifically, we plot this in a 3-dimension after converting the image to a grayscale. And this you can see in the scale of 0 to 255 pixel levels. What we intend is for each of these interference pattern, the crust and trough regions in the interference pattern. So there is a contour map on the base here, and our intention is to observe if there is a shift in the contour map between one scenario to another scenario. So these contour maps are of isometric intensity, and the software will process for things like grayscale, cropping for the image to be specific dimension, removal of noise and smoothing, and so on. Another thing to note here is that there's a lot of we should expect a lot of noise in the source itself, the laser source, for example, as well as the current source to the laser. So one good option is to run the 2 different scenarios by interleaving rather than doing the entire set at one time. So a quick note here is that the distance between 2 contours or the peaks represents the entire wavelength, because we know from the interference pattern that the successive crusts are actually regions where the crust meet the crust, and the troughs happen where the crust meet the trough, where there's a subtraction of the intensities. So here's a more detailed observation at the level of the contours on the baseline and their movement, and the first set is really for the lead of type B, and the second set of experiment is for lead of type 2B, and each of this is actually an average of several experiments, about 20 of them, and what we see is that a clear deviation of certain values, a fraction of the lambda between these 2 set of experiments. for the given distance of the observer screen. So this distance translates to around 2.1 milli-arc-seconds of subtended angle of additional deflection. So here's some more processing on image processing on this similar set of data. This time, instead of looking at the contour on the base plane and finding the deviation, so this processing applies a direct difference method. So the third image here really represents the difference between the first and the second scenarios, or rather the first set of average scenario and the second set of average scenarios. So clearly the experiments so far have shown that a change in the mass density of interfering object, like in this case that of a lead, creates additional deflection, right? So it's not about the absolute deflection, but the additional deflection because of a change in the density is observed. So although the experiment and this paper by itself do not claim the results one way or the other, it's really a precursor to what can be easily replicated and hence helping in the statistical results to weigh in on these observations. So you can find the details of the setup in the links below and some of the reference material used in this paper.